Continuous maintenance and reliability. Good morning, everyone. My name is Ilham Ainuddin, and I am your lecturer for the course Operational Management in the Business Administration program at Diponegoro University. Today, we will discuss an important topic in operational management, namely continuous maintenance and reliability. In modern organizations, especially in manufacturing, logistics, healthcare, and transportation industries, operational performance is strongly influenced by how well organizations manage their assets and equipment. Machines, systems, and infrastructure must operate reliably in order to ensure efficiency, safety, and productivity. However, machines will always experience wear and tear. Therefore, organizations must develop systematic maintenance strategies that allow operations to continue without unexpected interruptions. In today's session, we will explore several important concepts, including operational reliability, preventive maintenance, predictive maintenance, reliability centered maintenance, total productive maintenance, and key indicators used to evaluate reliability performance. By the end of this lecture, you should understand not only the theory but also how these maintenance strategies are applied in real industries. First, let us begin with the concept of operational reliability. Operational reliability refers to the ability of a system, machine, or process to operate consistently according to required standards over a specific period of time. In other words, reliability measures whether an asset can perform its intended function without failure. In operational management, reliability is extremely important because equipment failures can lead to production interruptions, increased operational costs, safety risks, customer dissatisfaction. In reliability analysis, several key indicators are commonly used. The first indicator is MTBF, mean time between failure. This metric measures the average time that a machine operates before it fails. The higher the MTBF, the more reliable the system. The second indicator is MTTR, mean time to repair. This metric measures how long it takes to repair a system after failure occurs. A shorter MTTR indicates better maintenance response. Another important indicator is availability, which measures the proportion of time that a machine is ready for operation. Finally, we also analyze the failure rate, which indicates how frequently failures occur within a given time period. It is important to understand that modern reliability management emphasizes continuous improvement, not just reacting after failures occur. Organizations must move from reactive maintenance to proactive reliability strategies. The first maintenance strategy we will discuss is preventive maintenance, commonly known as PM. Preventive maintenance refers to scheduled maintenance activities that are performed before failures occur. The basic idea is simple. Instead of waiting for machines to break down, organizations maintain them periodically. Preventive maintenance can take several forms. The first is time based maintenance, which means maintenance activities are conducted at fixed time intervals. The second is usage based maintenance, where maintenance depends on machine usage, such as operating hours or production cycles. The third type involves routine inspections and lubrication activities. Preventive maintenance offers several advantages. First, it can reduce unplanned downtime because problems are addressed before failures occur. Second, it can extend asset lifespan, allowing machines to operate longer. Third, it helps create more predictable maintenance costs. However, preventive maintenance also has some disadvantages. One major issue is over maintenance, where Machines are serviced even though they do not actually require maintenance. Another challenge is the lack of adaptability to real machine conditions. Because maintenance schedules are fixed, preventive maintenance is also less effective for random failures, which occur unexpectedly. For PM to be effective, several implementation principles must be followed. Organizations must first determine asset criticality, meaning not all machines require the same level of maintenance. Second, organizations must develop standard job plans, including procedures, tools, time estimates, and safety guidelines. Third, maintenance intervals should be based on historical failure data. Finally, organizations must ensure execution discipline, meaning maintenance schedules must be followed consistently. The next strategy is predictive maintenance, often abbreviated as PDM. Predictive maintenance is a more advanced approach that uses actual condition data from assets to predict potential failures. Instead of following fixed schedules, predictive maintenance monitors equipment conditions in real time. An important concept in predictive maintenance is the PF interval. The PF interval refers to the time between potential failure and functional failure. Potential failure occurs when early signs of damage begin to appear. For example, vibration levels may increase or temperature may rise. Functional failure occurs when the asset can no longer perform its intended function. The main objective of predictive maintenance is to detect problems during the PF interval. This allows maintenance teams to repair or replace components before total failure occurs. This strategy significantly reduces unexpected breakdowns. Predictive maintenance relies heavily on monitoring technologies. One commonly used technique is vibration analysis, which can detect mechanical problems such as imbalance, misalignment, or bearing wear. Another technique is thermography, which uses thermal imaging to identify hotspots in electrical systems or motors. Organizations may also perform oil analysis, which examines contamination levels and metal particles in lubricants. More recently, companies are using IoT sensors and AI analytics to monitor machine conditions in real time. These systems can track variables such as temperature, vibration, electrical current. Predictive maintenance provides several benefits. First, it enables data driven maintenance decisions. Second, it minimizes downtime because failures can be predicted. Third, it improves long term cost efficiency. However, predictive maintenance also has limitations. It requires initial investment in sensors, software, and technical expertise. The system also depends heavily on data quality. If the data is inaccurate, the predictions will also be incorrect. Finally, organizations must establish clear decision processes determining when maintenance action should be taken after alarms are detected. Another important approach is reliability centered maintenance or RCM. RCM is a systematic approach used to determine the most appropriate maintenance strategy for each asset. Instead of applying the same maintenance method to every machine, RCM focuses on understanding the function of an asset, possible failure modes, the consequences of those failures, and the most effective maintenance strategy. RCM focuses strongly on risk and impact analysis. For example, some failures may only cause minor inconvenience while others may lead to serious safety risks or major financial losses. RCM is widely used in industries where reliability is extremely critical. These include aviation, oil and gas, power generation. One advantage of RCM is that maintenance decisions become logical and cost effective. However, Implementing RCM can be challenging. It requires cross functional collaboration involving engineers, operators, and maintenance specialists. The initial analysis process can also be time consuming. Let us now briefly examine the typical steps involved in implementing RCM. The first step is defining the function of an asset. For example, a pump may be required to deliver a certain flow rate at a specific pressure. The second step is identifying functional failures. This occurs when the asset cannot perform its intended function. The third step is identifying failure modes, meaning the specific causes of failure. For instance, a pump may fail due to worn bearings, damaged impellers, cavitation, or leaking seals. The fourth step is analyzing the effects and impacts of failure. This analysis considers whether the failure affects production, product quality, safety, or the environment. Finally, organizations must choose the appropriate maintenance policy. Possible strategies include preventive maintenance, predictive maintenance, redesign, or run to failure. Another widely used approach is total productive maintenance or TPM. TPM is a maintenance philosophy that emphasizes involvement from all employees, not only maintenance technicians. In TPM systems, machine operators also play an important role in maintaining equipment. The ultimate goals of TPM are zero breakdown, zero defects, zero accidents. TPM consists of 8 main pillars. These include autonomous maintenance, planned maintenance, quality maintenance, focused improvement, early equipment management, training and education, safety, health, and environment. Administrative TPM. One of the most famous implementations of TPM can be found in the Toyota production system. After implementing maintenance strategies, organizations must evaluate their effectiveness. Reliability performance can be assessed using both quantitative and qualitative indicators. Quantitative indicators rely on technical data, such as downtime or failure rates. Qualitative indicators relate to organizational factors, such as maintenance discipline and work culture. Several important key performance indicators are commonly used. These include overall equipment effectiveness, availability rate, downtime frequency, maintenance cost ratio, failure trend analysis. Let us now discuss these indicators in more detail. One of the most widely used reliability indicators is overall equipment effectiveness, or OEE. OEE measures how effectively production equipment is utilized. It combines three dimensions: availability, performance, quality. The formula is OEE, lecture availability x performance x quality. If OEE is below 60%, it indicates very poor operational performance. If OEE is between 60% and 75%, the system is functioning but still requires improvement. If OEE is between 75% and 85%, the system is performing well. If OEE exceeds 85%, the organization is considered world-class in operational performance. Another important indicator is the availability rate. Availability measures the percentage of time that a machine is ready for production. Availability can be calculated using the following formula. Availability change is MTBF plus MTTR. This means availability increases when failures occur less frequently, repair times become shorter. High availability indicates a reliable system with efficient maintenance response. Predictive maintenance and reliability-centered maintenance are particularly effective at improving availability. Another useful metric is downtime frequency. This indicator measures how often a machine experiences downtime during a given time period. High downtime frequency may indicate chronic operational problems, ineffective preventive maintenance, poor maintenance discipline, Managers often use this metric for Pareto analysis, applying the 80-20 principle to identify the most critical failure causes. Maintenance performance must also be evaluated financially. One important indicator is the maintenance cost ratio. This metric measures the proportion of maintenance costs relative to asset value or production costs. If the ratio is too low, it may indicate under maintenance, which increases the risk of failures. If the ratio is too high, it may indicate inefficient maintenance practices. In manufacturing industries, a typical benchmark is 2 down to 4% of replacement asset value. Failure. Trend analysis evaluates whether reliability is improving over time. Organizations analyze patterns such as monthly breakdown counts, MTBF trends, cumulative downtime trends. If failure rates decline over time, the reliability strategy is working. If failure trends increase, it indicates deeper systemic problems. This analysis also supports strategic decisions such as redesigning equipment or upgrading maintenance systems. Maintenance decisions must also consider cost and benefit trade offs. Organizations must compare two main types of costs: maintenance cost, failure cost. Failure costs may include lost production, safety risks, environmental damage. Preventive maintenance is relatively cheap in the short term. However, predictive maintenance may be more cost effective in the long term. Organizations also evaluate return on maintenance investment (ISCHA or MEIs) to determine whether maintenance investments produce operational benefits. Let us now examine two real-world examples. The first example is PT Pertamina, the Indonesian state-owned energy company. Pertamina uses sensor-based predictive maintenance in its refinery operations. They also apply reliability-centered maintenance to critical assets and implement TPM in key operating units. As a result, the company has successfully reduced unplanned shutdowns and increased refinery availability. The second example is Toyota Motor Corporation. Toyota integrates total productive maintenance into the Toyota production system. Operators are responsible for performing routine machine maintenance. This approach, combined with continuous improvement practices known as Kaizen, has helped Toyota achieve high OEE and minimal downtime. To conclude today's lecture, let us summarize several key points. Operational reliability is a fundamental factor in achieving long-term competitiveness. Different maintenance strategies, including PM, PDM, RCM, and TPM, complement each other. Reliability management must be data-driven and supported by cost-benefit analysis. Most importantly, successful implementation requires a strong organizational culture that prioritizes maintenance and continuous improvement. When organizations successfully manage reliability, they can achieve higher efficiency, improve safety, and sustainable operations. I hope this session has helped you understand how maintenance strategies contribute to operational excellence. Thank you very much for your attention. If you have any questions, we can now begin the discussion.